Welcome back, Physical Science 20. This is the beginning of the next unit, Properties of Waves. So we look at PW1, Properties of Waves 1, investigate the properties and characteristics of 1, 2, and 3-dimensional waves in at least 3 different media. So the topics we'll be looking at here, PW1.1, mechanical waves. We'll be looking at properties. So that'll be what this video is. PW1.2, we'll look at the speed of mechanical waves. 1.3, we'll look at interference and diffraction. And then 1.4, we'll look at light waves, look at their properties and their speed, and also look at interference and diffraction of those waves. And then we'll look at a couple of wave applications at the end, in particular the Doppler effect, which I'm sure you have experience with. So PW1.1, mechanical waves, it's a fairly big section because there's a lot of terminology we need to discuss here right out of the gate. So recognize that scientists understand waves as the transmission of energy originating from a vibrating source that determines the frequency and amplitude of the wave. That's a lot of key things right in that sentence right there, as we'll see. Number 2, communicate information about the properties and characteristics of waves using appropriate terminology, including medium, pulse, vibration, cycle, periodic motion, frequency, period, amplitude, phase, and wavelength. So there's some of the terminology we'll be looking at. Then identifying characteristics of transverse and longitudinal waves, including crests, troughs, compressions, rarefactions, and the relationship between the direction of the vibration and energy transfer. So water waves, sound waves, and waves that were traveled on a rope or a spring are types of what we call our mechanical waves. Mechanicals mean that they need something in order to carry the wave energy itself. So if I'm looking at a slinky wave, I need a slinky. If I'm looking at a rope wave, I need a rope. If I'm talking about a water wave, I need water. If I'm talking about an air wave, I need air. So we need something to transfer the energy in that wave. Because many other waves cannot be directly observed, mechanical waves can serve as models. The first type of wave, transverse waves. The disturbance shown in this figure right here is a wave pulse. So one kind of flick of the wrist, you've often done that with a rope, kind of flick it in one way and a pulse is sent down the length of it. That wave pulse is a single bump or disturbance that travels through the medium. If the wave moves up and down continuously at the same rate, a periodic wave is generated. So if I keep making this pulse, moving my hand up and down, it's a periodic wave. It repeats a pattern over and over again. It's like the periods of the moon, repeats a specific pattern over and over again. Notice in the figure that the rope is disturbed in the vertical direction, but the pulse travels horizontally. A wave of this type is called a transverse wave, and it's one that vibrates perpendicular to the wave motion. So as you can see, the waves are moving this way, and yet the vibration is up and down. So moving my hand up and down, and the wave moves side to side. So of course that makes a right angle here, right? This and this makes a right angle. So that's what we would refer to that in math class as a right angle. Arrow moving this way, arrow moving this way, 90 degrees. So transverse wave means vibrating in one direction and the wave goes 90 degrees from that direction. Longitudinal wave, in a coiled spring, for example, you can create a wave pulse in a different way. If you squeeze together several turns of the coiled spring and then release it, pulses of closely spaced turns will move away in both directions, as shown in the figure on the top of the next page. So if you have a spring and you compress it, then let it go, it expands out. So I'm compressing it, it expands out. Or if I stretch it, then let it go, it goes back together. So however I move it, stretch it or compress it, it moves in the same way. It's parallel, so that is referred to as a longitudinal wave. So the disturbance is in the same direction, or parallel. So here we had perpendicular, that's transverse, parallel is longitudinal. And of course that longitudinal picture is here on the next page. The areas close together are called compressions, and the areas that are far apart are called expansions, or often in physics we call that rarefaction. So compressions and rarefactions. Sound waves are longitudinal waves, which makes sense because, as we'll see here later on in this section, that vibrating air molecules hit our eardrum, and then we perceive that as sound through a few other steps. Fluids usually transmit longitudinal waves as well. Wave properties. Many types of waves share a common set of wave properties. Some properties depend upon how the wave is produced, whereas others depend upon the medium. So how it's produced, and sometimes it's the medium. Amplitude, first of all. How does the pulse generated by a gently shaking of a rope differ from the pulse produced by a violent shake? The difference is similar to the difference between a ripple in a pond and an ocean breaker. They have different amplitudes. Therefore, the amplitude of a wave is the maximum displacement from where it was at rest. So if this is rest position, and then if I look at making a flick of the wrist here, so a transverse wave, the amplitude would be this. How far away from it is from rest position? So the amplitude would be here. Or if I'm looking at this wave, this would be the amplitude. This would be the amplitude, amplitude, amplitude. How far it is from the rest position. So rest position is an amplitude of 0. Shaking it or whatever, it has a certain maximum distance from that two-part. Two similar transverse waves having different amplitudes are shown below right. So that's leading to this diagram. So this one has a larger amplitude than this one, obviously. Energy of a wave. A wave's amplitude depends upon how, so the amplitude depends how big you flick your wrist or how you compress the springs together. It doesn't depend upon its speed, it depends how it's made. More work must be done to generate a wave with a greater amplitude. For example, strong winds produce larger waves than those by gentle breezes. Waves with great amplitudes have greater energy associated with them. Whereas a small wave might move sand on a beach a few centimeters, a giant wave can uproot and move a tree. Wavelength. Rather than focusing on one point of a wave, imagine taking a snapshot of the wave so that you see the whole wave in an instant in time. The figure on the previous page shows each low point called a trough and each high point called a crest. Well, the previous page, what I really meant is this one right here. I think in my original notes I must have had this on the next page. So here we have a crest and a trough. The crest is the topmost part. Trough is the bottommost part of a transverse wave. Now, if I'm looking at what is wavelength, so if you look over here, it's the shortest. Then if you flip to the next page, shortest distance between 2 points where the wave pattern repeats itself is called a wavelength. Crests are spaced by one wavelength. Troughs are spaced by one wavelength. And we use a specific symbol for wavelength, a variable. It's the Greek symbol lambda. So it kind of looks like that. Kind of a curvy line with that part. Kind of looks like a guy running to the left with no arms. So if we look over here, this would be a crest, this would be a crest. So one wavelength represents where the pattern begins to repeat. So this would be so crest, crest. So that's one wavelength. Or if I take a look at trough, trough, the same distance as over here. Or any corresponding part. So if I'm on the upside, if I'm comparing this point, on the upside in the middle, on the upside in the middle, there's another wavelength. So all of those values are equivalent. You can pick different parts. So it's the shortest corresponding points on a wave as you're moving. All right, so that is what a wavelength is. Phase. Any 2 points on a wave that are one or more whole wavelengths apart are said to be in phase. So those corresponding points again, if they're corresponding points and they're how many whole wavelengths apart they are, whether they're 1, 2, or 3, those are said to be in phase. Particles in the medium with opposite displacements of velocities are 180 degrees out of phase. A crest and a trough, for example, are out of phase in exactly 180. Two particles in a wave can be anywhere between 0 and 180 out of phase with each other. So if I'm looking back here, this point and this point would be in phase. This point and this point would be in phase with each other. However, this point and this point would be out of phase with each other. So in phase, easy to see the exact corresponding points. Period and frequency. What I think we'll do is we'll stop right there. We're over 10 minutes in the video, and we'll come back and do part 2 at some more wave terminology.